And next presentation is by Zachary Geraerts. He will be presenting an investigation of the catalytic reaction, so some chemical reaction facilitated by a catalyst.
Okay, hi. So my name is Zach. I'm sure you guys are familiar with me by now. This is good. So today I will be presenting my results on reductive nitrosylation, molecular dynamic simulations. So what is reductive nitrosylation? Well, it is a reaction where nitric oxide gets oxidized to nitrous acid, which then ends up reducing some metals such as iron. And so this process can be thermodynamically modulated depending on pH and other factors that may impact the electrostatics of, let's say, the transition metal. However, my focus will not be on the thermodynamic properties, but rather the rate at which the reaction proceeds based off of dynamics. And in particular, I will be modeling the second step here and the third step. Okay, so why should you care? Well, nitric oxide is a very common cell signaling molecule in many life forms. And its interactions are principally with cofactors that are metallic, so like metalloproteins. So there is some physiological relevance to nitrosylation. What I will be attempting to do with these simulations, and I kind of briefly mentioned it, but it's to figure out what the optimal angle of collision is in order for the reaction to proceed. And the molecule that I will be using to exemplify this is this nitrosyl protoporphyrin 9, iron 3, coordinated with imidazole in the presence of hydroxide. Okay, so I performed molecular dynamics using VASP. I also used density functional theory to determine some density of states and calculate the CHEM orbitals. So a couple of things real quick. The spin states in all of my models are singlet, so I don't have higher order spin states. And for the actual molecular dynamic model, it is charge neutral. All right, so this just shows the geometry optimized structure for my first model. The thing to keep in mind is that the HOMO has electron density on the porphyrin ring, whereas the LUMO has electron density on the nitrosyl ligand. If we look at the Serre transition of this particular model, we see that these transitions are dominated by molecular orbitals that have charge density along the porphyrin ring. These are pi-to-pi star transitions that are commonly observed in porphyrins. All right, so let's look at a molecular dynamic simulation where the hydroxide kind of grazes by the NO. As you can see, we don't get a reaction. That may not be entirely surprising. But when we look at the electronics, it will differ from the model I had shown you before. So here, our HOMO, we have charge density now on the hydroxide, whereas the LUMO, once again, has some charge density on the nitrosyl ligand. If we look at our Serre transitions, here, while our HOMOs, where the transitions arise from, are delocalized in the porphyrin ring, some of the LUMOs actually have some charge density on the ligands. So there's a slight difference there. Now, when we look at a molecular dynamic simulation where the hydroxide collides directly with the nitrosyl, what we've noticed that, hey, we've not only connected, we've formed a bond, and it's dissociated from the iron. So we formed our nitrous acid. So what does that look like electronically? Well, our HOMO has some charge density on the iron center, which is slightly different from what we've seen before. We have charge density now back on the porphyrin rings for our LUMO. More interestingly is that if you recall, with our Serre transitions, that those were in the LUMOs partially localized on ligands. It's not anymore, it's back on the porphyrin ring. Another interesting thing is that if you plot energy as a function of time during the molecular dynamic simulations, notice is that there's this huge gap, or drop, I should say, in, say, potential energy or increase in kinetic energy for the direct collision. Intuitively, you would think this may actually correspond to either a bond forming, breaking, or some reorientation of the molecule being a kinetic barrier. However, at these time points, there are no ionic positions or atomic positions that can be related to forming bonds or breaking bonds. All right, so in conclusion, the hydroxide nucleophile here, when it directly collides with the NO, does proceed with the reaction. This is kind of supported that the reaction actually has happened by the reorganization of the electronics between where it did not undergo reaction and when it did. And one could state that the reaction appears to be thermodynamically favorable, but that may be an artifact in how the simulation was ran. And there's plenty of future work one could do with this on a kinetic standpoint or a thermodynamic standpoint. But one would like to relate reductive nitrosylation susceptibility to the 3-iron-2 redox of, say, proteins.
Okay,
Questions?
let's thank Zach for interesting presentation.